Hello, everyone, and welcome on the webinar on topic on architecting multi-threaded robotics applications in C++. I hope that all of you will have a very enjoyable time while I give my talk on this topic. But before diving deep down on the role of software architect and understanding how the architecting of multi-threaded robotics applications in C++ works, I would like to share with you a very short quote, which probably was said by many software engineers that go through this process. The quote states is that the developing of impactful software requires more than writing fast, concise, and correct codes. What we try to say with this quote is that many times software developers tend to concern themselves very much with fulfilling in the requirements according to the machines or the computer that they're programming in. They forget most of the time that the user of the software is also a human being and they have all their own requirements, which in most of the cases, they don't know how to express them in the technical language. Therefore, there is this process of architecting, which brings many stakeholders together and clears the path of how to develop an impactful software, which also will fulfill in the requirements that are from the technical side, but at the same time, have an impact on society. Before taking a deep dive, I would just like shortly to introduce myself. I am Arian Ajdari, and I have studied computer science at Technical University of Kaiserslautern. My master thesis was concerned to develop a framework which facilitates the development of multi-threaded applications in Rust2, which is written in C++, and mainly this thesis has inspired my talk in the CppCon. Currently, I am employed as research fellow at Fraunhofer IESE, but I'm also open for new job opportunities. To make this a more enjoyable experience for you, I would like to share some trivia or the mistakes that I made during my programming days. So in JavaScript, I accidentally overridden the object, which is like the base class of all other classes which derive from. And I lost 3 days searching from object.keys methods. I was not aware that I was overriding a base class from JavaScript. I also tried Unreal Engine 4 on a very old computer, and I lost a day trying to open a door in-game. And finally, what drove me to do my master thesis on this talk was my love for Formula One and motor racing. So what is today's topic, what we are going to talk about? In the beginning, we are going to set up the context where we clear some of the definitions, which will prove very useful for this talk. We are going to talk about what is software architecture, software architecting, and how the software architect binds these two things together. Then we will take a deep dive in how robotics application and C++ work together. After we understand this point, we get in the boots of the software architect and we receive a problem. We then explain how the problem is affected from the hardware and software stack and see the arising challenges. After this point, we reformulate the problem by combining software architecting, robotics engineering, and multi-threading, and we propose a solution which is called Lambda. At this point, after we finish the implementation of Lambda in C++, we do a proper evaluation to understand how the solution is working, and we provide the context on how we could evolve our solution further. Please make sure that to also use the Q&A capabilities in order to ask any questions, which I will be more than happy to answer after I finish my talk. So what is software architecture? Software architecture, in a nutshell, presents a blueprint or the organization of software systems. It provides a structure to ensure that quality properties have been fulfilled. If you would like a more formal definition, we could define it as the software architecture of a system is the set of structures needed to reason about the system. These structures comprise software elements, relations among them, and properties of both. What is a really interesting mantra about software architecture is that every software system, or in our case, every program that we write in C++ ends up with a software architecture. The only difference is whether it is the software architecture that we want or not. A good software architect makes sure that he knows what kind of software architecture he wants, because at the end of the day, it gives him the possibility to predict its properties. The process of software architecting comprises of these elements. In the beginning, a customer comes up with a particular idea for a product that he would like to be developed for him. Then we formalize this idea through system requirements where we sign the documentation and make sure that we understood what the customer wants. Then from these system requirements, we make sure to extract the most important requirements which shape our software system. And in the technical language, we call them architecture drivers. When we provide the solutions which solve the system requirements, the main ones which we call architecture drivers, we arrive to the architecture solutions. And then we start implementing our solution with targeted technologies, in our case being C++. And at the end, we make sure that we deliver the product to the customer and do the maintenance by ironing out the bugs and doing general improvements. So who are we in this case? We are software architects, a role which is very prominent in today's development world. It is a role that it cannot be taught directly, but it is the role that the particular programmer or software developer evolves into. By having an experience with working with different stakeholders, mainly I have listed the stakeholders here, such as business, developers, project manager, marketing, a particular person can develop into the role of software architect. Software architect serves as the central hub of bringing many stakeholders together, understands the particular language, how they communicate, and make sure that all the goals of a particular software system have been achieved. To give you a short tip, mainly in the most of the cases, a software architect becomes someone who is the best developer in the team, who understands the targeted technology the best, and also has a good combination of hard and soft skills, mainly to understand different stakeholders. So how about now the C++ and robotics application? Software that usually runs a robotics application has facilities for low-law access, which automatically makes the suitable candidates for C and C++. Many frameworks have emerged to support the development of robotics applications. One of the most prominent one is Robot Operating System. ROS2 is open source. It is based on publish-and-subscribe pattern and has support for different middlewares facilitating communication and targets newer C++ version. If we would run through ROS2 the process of architecting, we could have it for idea, for example, a customer which would like to have a robot which does SLAM. Then we would extract system requirements. We would know which technology to use. After that, we would derive architecture drivers and understand that the particular sensors and their implementation are the most important. We would do the implementation, and finally, we would deliver the product. So now we will dive in the real life problem. We work in a company which builds robotics applications, and the business, which is stakeholder, as we mentioned earlier, comes up with a signed up contract where a particular client would like to have a robotics application that does SLAM, simultaneous localization and mapping. Now we, as software architects, we know what kind of people we have on our team. We have robotics engineers which understand hardware, therefore know that multi-threading can be utilized for performance benefits. However, we also understand that the correct utilization of multi-threading is a hard process and error-prone. Therefore, we as a software architect come to the conclusion that multi-threading is a significant architectural decision. So in our case, this is our architectural driver. And therefore, we need to rely on us, in our case, being software architect, to correctly apply multi-threading. So as a software architect, we would like to look at the whole development stack and hardware and to understand with what we are dealing. From the hardware point of view, we are dealing with CPU and main memory. And inside CPUs, we have different cores which have the dedicated caches, in our case being L1 and L2 caches, whereas all cores make sure to share L3 caches. And the communication between the CPU and main memory is facilitated through bus. Software architects understand that the proper utilization of caches and high cache hit makes sure that the application is executed as fast as possible. From the operating system point of view, we understand that we have a particular scheduler, which makes sure that every process that we run, the logical process, gets an execution time, which is decided by the way that the scheduler is programmed. On top of that, we also have synchronization mechanisms, which make sure that we don't have race conditions or make sure that the particular process is executed the way that we meant. And finally, we have the processes themselves, each of them having text, data, the region for the data that is initialized to 0 and stack, and all the processes that are logically declared as threads, they share the common heap. If we zoom inside a particular process, we can see that when we run a ROS2, we have 3 layers of ROS stack. On the top of the layer, we have the layer which is called application layer and is directly accessible by robotics engineers. They can define their publishers and subscribers. Publishers have the role of sending a particular message at the specified time interval, which is the one with timers. For example, they can say that the temperature sensor can publish its temperature every 1 second. Subscriber does the reverse of publishers. They subscribe to a particular publisher and make sure to receive this information and process further. As a further abstraction, we have services where we can perform a short-term action, and actions are where we can perform a long-term action, something that needs a longer time to be calculated. As far as managing publisher, subscribers, actions, and services are concerned, we have callback groups. Under this, on a more low level, we have executor, RCL, CPP, and RMV, which are developed by ROS2 community, and they make sure that by not taking account which particular middleware works, we can make sure that always the publisher, subscribers, and other constructs which are provided to the end user are usable in an agnostic way without making worrying, whereas publisher or subscriber come from different systems. And all of the rest is make sure to be run in C++ and also using threading library. Challenges. So now with you that you are listening, most of you coming from the software development backgrounds, we can see that after explaining the stack, hardware and software, we can see that many challenges arise. In order to utilize multi-threading in robotics application, a fine knowledge of C++ is required. A fine knowledge of the whole software and hardware stack is required, and a fine knowledge of how multi-threading is handled is required. So as software architects, we would like to have a short reformulation of this problem and try to see how the robotics engineer thinks about multi-threading, not how a particular software engineer thinks it. So we come to an understanding that robotics engineers would like firstly to identify the parallelization candidates. So it means he sees a particular function and thinks that we can use multi-threading to make it execute faster. Then robotics engineer would like to assign some resources, how many cores he would like to use. He would also like to assign priorities, saying that, okay, this particular operation is a high priority, it needs to be executed as fast as possible. He would also like to have the possibility of deciding the scheduling, how the particular task would be scheduled, and would like to perform the implementation. And in the end, have parallelized code as its output. Furthermore, we understand the software architects that ROS2 supports multi-threading. This is the output of a simple perf script which shows CPU utilization inside ROS2 process. When we run as a single threaded, we see that the CPU is utilized much less, whereas on the right side, we see that the CPU utilization is much higher when we spawn many threads. Now we reformulate the problem. We say that while robotics engineers are good at modeling robotics application, they struggle to understand software engineering related concepts. They struggle to understand low-level multi-threading concepts, and they struggle to understand C++ on low level and its relationship to hardware. Furthermore, C++ offers specific parallelization libraries tailored to ROS2 requirements, and pthread in our case is too level, and thread library for C++ is too abstract for our needs. Therefore, we arrive to the conclusion that architecting robotics application is challenging because many different aspects of software development intermingle, as we explained at our software stack. We also stated that development stack includes both hardware and software, and robotics engineers mainly specialize in their own subfields. Therefore, we developed Lambda to overcome overlapping challenges in robotics engineering, C++, and in architecting robotics applications. How about quality properties? Lambda tackles the following quality properties, not all of them, but the mainly ones that are specified in the standard ISO 25010. And we mainly deal with compatibility, performance efficiency, reliability, and maintainability. So to summarize, what should our technical challenges and quality properties which need to be fulfilled? We need a tool that fulfills quality requirements within a correct level of abstraction, providing linear thinking model while developing multi-threaded applications. To simplify, this quote means that robotics engineer should have a tool or library written in C++, which satisfy above quality requirements, also the technical requirements of being fast and efficient, and being able to develop multi-threaded applications, but having a linear thinking model. So robotics engineers should not be aware at all that they are using multiple threads. They should be thinking that they're only using a single thread, whereas multi-threaded operations are handled in background. So our solution, Lambda, tackles all stacks that we mentioned, software and hardware. So in the scope of software stack, we take advantage of C++ facilities like our templates, standard libraries, std thread. We take advantage of embarrassingly parallel operations, whereas for the operating system, we take advantage of real-time kernels. We take advantage of scheduler type, and we take advantage of processor affinity. Whereas from the hardware point of view, we take advantage of multicores, we take advantage of hyperthreading, and take advantage of caches. But what about other approaches? As software architects, we sure have come upon many different solutions which mainly can solve the problem, but why we are not using those and are instead developing our own solution. So during the research, we came to the conclusion that while solutions such as OpenMP solve our problems, its interface is not very catered to the needs of robotics engineers. And since ROS2 is written in mind by using higher versions of C++, OpenMP is just a set of compiler directives, which would make the development process for robotic engineers much harder. Whereas, for example, MPI is a solution which targets multiple computers, whereas in our case, we would like to target only the threads found in one computer. So our solution does the identification of important parameters. It implements the parallelization component in C++. It implements the benchmarking component in C++. It also has some Python bindings. It provides a visualization component, provides some input scripts. It provides the capability to parallelize functions and integration in ROS2. The important parameters which were identified by our frameworks are threads number, logical in our case, scheduler type, affinity, and parallelization approach, which can be the direct implementation of std threads, which uses pthread in most of cases as native handle, OpenMP, etc. Furthermore, Lambda relies on these two performance-related metrics to measure its efficiency: average execution time and deviation between average execution time and worst-case execution time. As far as measure of its efficiency, we are going to explain this in detail at the evaluation chapter. So this is the conceptual solution of how we thought as software architects and how we are going to develop it. So at the center, we have Lambda, which has pre-parallelized mathematical operations. So we identify which of the operations are most commonly used by robotics engineers, and we parallelize them. Furthermore, we also provided a benchmarking tool which robotics engineers can use to find out which parallelization options provide the best result, which provide the best trade-off. And in order for robotics engineers to use our solution, they only need to provide input data, in our case in being matrices written in std vector, and a couple of parallelization options which tell Lambda with what kind of the settings should the parallelization happen. Lambda also can be embedded inside ROS2 application or can be compiled as a standalone C++ application with CMake lists, or you can use ROS2 Qualcomm build. And in the end, we have parallelized binaries as an output. Before we explain how parallelization works in Lambda, we just would like to take a short amount of time and explain how manual parallelization would work with pthreads. The reason why we use the native handle of std thread library is to explain how complicated this process is and how careful we need to be when we want to provide specific settings of how the parallelization should happen. So we need to make sure that first we spread the data equally to all threads. Then we need to make sure that we do a proper counting of CPUs. Understand that even though we may have 4 physical cores here in the API that is provided, we need to make sure that we are counting them as logical cores. We need to make sure to check the boundaries of data. And all of these things are things that they can go wrong. The things that we are trying to evade and make sure that the robotics engineers don't deal with. So this code is basically transformed in many classes and enums which software robotics engineers could use. So we provide a simple parallelization strategy enum where they can choose what particular parallelization strategy would they like to use, in our case being pthreads or OpenMP. They also provided a serial where they use only one thread, only for benchmarking purposes. Then we overloaded the string operator to make the API easier to understand, so they can specify the number of threads and just write the int 4_thread, so everybody knows what that particular number 4 means. It's very similar to the chrono library that uses the milliseconds or nanoseconds. Then we provided a simple enum, which tells whether we would like to use affinity. And this is the base class that each mathematical operation makes sure to inherit and implements the methods. This is all done in the background. The robotics engineers have no idea that this is happening. They have the linear thinking model where they can continue programming their robotics application and have the best efficiency when executing their mathematical operations. So this is when we would like to use to multiply two matrices by Lambda. So we just create a simple struct, which is called settings, and we provide inside the options that we would like to use. In our case, we would like to use 4 threads and set 70 priority inside scheduler. We would also like to use affinity, and our parallelization strategy is pthreads. Then we just call the multiply parallel. We provide what type of the data we would like to use. We provide input data in form of matrix A and matrix B and settings, and the result is saved in the matrix B. We can think this as a source destination, or if users would like to save the results on another matrix, they can also provide it as a result as an argument after matrix B. Here we have our benchmarking component where users can use our generators to generate dummy data. They provide data type they would like to use, and the sizes 100 and 200 show that they is going to generate 2 matrices, one of them being 100 by 100 and the other one 200 by 200. They can also provide a vector of different settings that they would like to use. So we would like to compare how 4 threads in using pthreads as parallelization strategy compares to the serial execution, whether we get good results when we do a particular operation. And finally, we just that we would like to execute all the benchmarks and set milliseconds as time format. Then the results that are generated by the benchmark component can be fed in inside the script, which is written in Python, and the users can see which particular setting is their best match for the results. So we can see that as far as using pthread and matrix the size of 2000 by 2000, the best result is to have a priority of 21, having true set for affinity using pthreads and 4 cores. These are Python bindings that are written in C++, where users can find out how big is the data set, how many iterations were performed, and what is the minimum, maximum, and average execution. This is just a struct that helps us to extract the information of how quickly operation is finished. So we have the average result, and we have minimum, maximum, and we also have the iteration number, how many times a particular operation has been run. And this is the code that is then compiled as a dynamic library that can be loaded by Python. And we can execute this operation also as a script written in Python, even though they are compiled as dynamic library, and the code that is run in hardware is C++ code. The reason why we also provided Python bindings is because the ROS is very popular with Python as well, but we wanted to show that when the speed and efficiency are concerned, we would like to do the parallelization using Lambda in C++. And now we also have some input scripts. One of them, which is hardware information, it just gives us the information of how many physical cores, total cores, max frequency, minimum frequency, and the current frequency that we are using. This information is very useful for robotics engineers. They can use this information to find out which settings they would like to use with Lambda when performing parallelization. This is a feature where robotics engineers can just specify a for loop and what kind of particular operation will be performed. If they have to do many multiplications or divisions or additions, they can just specify that particular operation that be performed, and this makes sure to convert this operation in parallelized form. All of the functions that's created, they can be fed directly to the parallelization component or benchmark component, and finally displayed using the visualization component that we explained. So currently we support basic linear algebra operations such as multiplication, summation. We also support grayscaling, which is a very common operation used in image processing, where we turn a particular color pixel in its grayscale equivalent. And we also do pixel extraction by choosing which particular region we would like to use. And as far as specific operations, we have Bresnaham 3D, which is the fastest way of finding the shortest line between two particular points in 3 dimensions. We also have static map, which is used in SLAM, and we have forward kinematics, which is used when we have a particular robot with joints and we would like to calculate its movements. And here in this slide, we have explained how ROS2 is integrated, how Lambda is integrated inside ROS2. So we package it Lambda as a ROS2 package by using the CppCon build system. So if a particular robotics engineer would like to use Lambda, he needs to make sure that he creates a ROS2 application by using ROS2 create command. After that, the robotics engineer creates folder structure for its files, and in order to implement the desired functionality, they set up also package properties, and finally they just put an inclusion for Lambda package inside CMake lists, and Lambda is ready to be used in ROS2, just the same way that it can be used standalone without ROS. In order to find out whereas this solution presents improvement, we make sure to have a very good evaluation. So for operating system, we use Linux Ubuntu with standard kernel. That is where ROS2 is implemented. We use a hardware of having 16 gigabytes of RAM, Core i7 CPU with 6 cores, and 4.8 gigahertz of turbo boost. Our evaluation goals were to see whether technical requirements, which are efficiency and speed, and the quality requirements that we mentioned earlier, we would like to see whether they have been properly reached. And we did two types of evaluation. We did the quantitative evaluation and qualitative evaluation. In the scope of quantitative evaluation, we have average execution time and deviation between average time and worst case execution time. And finally, in the scope of qualitative evaluation, we have interview with experts and academics in robotics. So this is the average execution time where we executed a particular operation, and many times, in our case, it's 100 times. We averaged the times and we did them during the normal load. That means that was no process running in the background. So we see that Lambda with its settings provides a good improvement when compared to the serial. It is very similar to the execution of OpenMP as far as multiplication and summation is concerned. The reason why Eigen is slower in grayscale and blue channel operation is because the Eigen, in this particular case, is not able to figure out the proper order of operation and cannot parallelize it, just that he can do in the multiplication and summation. It is possible also to make Eigen run much faster, but it needs tweaking from software developers, which is against our goals that we set up in the beginning. We want a solution for robotics engineers that just works out of the box, not having the need to tinker with it or go in low detail and figure it out why it's not working. So now for the next average execution time, we have the same benchmark with the same iteration number, but in this case, we are using a high load. And in our particular case, high load means a YouTube video 4K running in the background. So we see, of course, the execution time rises because the scheduler assigns some time to that YouTube video as well. But we see that when we compare Lambda with OpenMP, we have comparable results. So as far as the efficiency and speed is concerned, Lambda fulfills our expectations. Here we have the deviation, which we calculated using maximum minus minimum divided with average. And what we try to capture with this particular equation is that when we have execution with multiple threads, it may happen that particular threads are swapped out and put to rest. And we wanted to see how many times the particular threads are swapped out and swapped in for the execution. The goal is to have as low as possible deviation, which makes sure that the CPU has been always utilized to do a particular operation that we would like to do. We see that when we use Lambda with no settings, we see that it may happen to have high deviation, but when we use Lambda with priority or affinity or both in the combination, we see that the deviation is much lower. This is also much more exaggerated when we have to do with the high loads. We see that Eigen has trouble keeping up because the cores the logical threads get swapped out many times, whereas when we use Lambda with affinity, we see that we have lower deviation. One interesting thing is that serial has also a very low deviation, and this comes for the very reason that serial is the execution in only one thread. So we have lesser candidates that can be swapped out in this particular case, and that's why the serial execution is always stable. And as far as the qualitative evaluation is concerned, we did interviews with experts in robotics field, with 6 of them in total. They have stated that the benefits of our framework significantly outweigh the effort for its integration. They stated that they would like to use it in their daily work, and they would consider replacing some of the operations with the pre-parallelized operations in Lambda, but they also showed some doubts about whether Lambda currently supports many operations. But this is the point where we would like to evolve even more our solution as software architects. So we would like to add more mathematical operations. We would like to add synchronization support and real-time support. So during this talk, we got the chance to learn a lot about software engineering related concepts. We learned many definitions. We understood the role of software architect. We explained the real life problem that we were facing. We understood the whole stack. Then we found out that there are many challenges of utilizing properly multi-threading. We made sure to reformulate the problem from the point of view of robotics engineers. Then in order to solve this problem, we devised a solution called Lambda. And in the end, we provided evaluation. So on this slide, you have my contact. You can always contact me through email or number. And on the right side, it's my mentor that helped me to write my master thesis and also guided the process of building the slides of CppCon. And I would like to say thank you for listening. I hope that you had an enjoyable experience and you learned a lot. And I would be happy to take your questions.